In the previous movie, we rigged a shoulder for our character along with the appropriate stretchability and controls. In this movie, we'll connect the arm to the rest of the body and then clean up the rig using our rigging checklist. Start by opening the file Character Rigging, Part 27 Start, or by using your own file from the previous lesson. We'll start by connecting the shoulder to the body. Group all the elements of the shoulder together into a left shoulder group and parent it to the EMMA root transform control. Then group everything under that, except for the control curve itself, into a Do Not Touch group. Next, we'll connect the shoulder to the rest of the torso. Although we're technically crossing from one body part to another, we're actually going to constrain the shoulder directly to the torso, rather than using intermediate locators like the neck in Part 6 or the leg in Part 18. This is because this shoulder geometry is pretty much custom fitted to this body. First, point snap the pivot of the left shoulder group to the shoulder bind joint we first created in Part 2. Remember, this is the joint that drives the torso's spline IK curve at the shoulder level. Now parent constrain the left shoulder group to the shoulder bind joint. The shoulder follows the torso when we move it. Next, we'll connect the IK arm to the shoulder. First, group the entire left arm into a left arm group and parent it to the EMMA root transform control. Then group everything under that, except for the IK Viz group, elbow control, and FK control, into a Do Not Touch group. Group the left upper arm IK joint, left upper arm to elbow disc start loc, and left arm length start loc together. Rename the group Left Arm Base IK Const Group. Move the group's pivot to the upper arm joint. This time, we will create a new locator to constrain the arm. Rename it Left Arm Shoulder Space Loc. Point snap it to the left shoulder end result joint, and then parent it under that joint. Now point constrain the left arm base IK const group to the locator. Like the leg, we'll also have to group the arm result joints into a left arm result const group. Move the pivot to the upper arm joint, then point constrain it to the shoulder as well. The IK arm now connects to the shoulder and by extension, the torso. When it comes to the FK arm, we'll want it working in multiple spaces, just like how we rigged the leg in Part 18. However, before that, we're actually going to add one more control. As we've noted a few times before, the arm's ability to twist and turn so easily can create some interesting, difficult to predict situations. Notably, it's easier to get into a gimbal lock situation around the shoulder than it is on any other part of the body. Recall that gimbal lock is a situation that occurs when rotating in one direction causes two axes to lie on top of each other. Unfortunately, no matter what rotation order we choose for the upper arm, we're going to run into gimbal lock scenarios for pretty common arm movements. To mitigate this, we're going to create a special gimbal correction control aligned to the upper arm. Create a pair of circle curves. Position them like so. The smaller circle will give us a clear indication of the direction of our gimbal correction axis. Freeze the transforms on both, then enable the shapes display in the outliner. Select the shape node of one circle and control select the other circle, and then use the parent-r-s mel command to parent the first curve's shape node to the other to create a compound curve. Rename the control left arm gimbal core control. Now point snap it to the upper arm. Rescale and reorient it so it looks like this. Freeze the controls transforms again. Parent your gimbal correction control under the left arm group, and then parent the FK arm under that. We also need to extend this effect to the result arm space, but without interfering with the arm in IK mode. Create a group around the result joints via the Edit menu, but this time make sure to turn off Preserve Position. This will ensure the result arm underneath it won't flip due to the non-matching spaces. Rename the group Left Arm Result Gimbal Group. Move the group's pivot to the upper arm joint. Then select it and the gimbal correction control. Open the node editor and show the connections. Create a blend colors node named Left Arm Gimbal Core Toggle. Connect the gimbal correction control's rotate attribute to the blend node's color 2 attribute. Set all the color 1 attributes to 0. Then feed the output of the blend node into the result const group's rotate attribute. Finally, middle drag the left arm settings control into the editor and drive the blend node's blender attribute by the current IK/FK mode. Now you can use the gimbal correction control to rotate the FK arm, but you can also rotate the upper arm independent of that, allowing you to correct for gimbal lock situations. Add the new control to the arm's IK layer and connect the left arm settings control's FK visibility attribute to its visibility. Next, we'll group the FK controls to themselves in a left arm FK const group, much like we did for the leg. Point snap the group's pivot to the upper arm joint. Then point constrain it to the left arm shoulder space loc. Now the FK arm follows the shoulder. We just need it to rotate in multiple spaces. Duplicate the existing left arm shoulder space loc twice, and rename the duplicates left arm body space loc and left arm root space loc. Parent them to the torso's Do Not Touch group and under the EMMA root transform control respectively. Orient constrain both the left arm FK const group and the left arm result const group to each of these. Now you can adjust the constraint values to change the space the FK arm acts in. Create a new attribute on the left arm settings control node called FK rotation space. And use driven keys to drive the constraint appropriately. Refer to the techniques used in Part 18 for more details. Now we can fully control the way the arm interacts with the rest of the body. You'll notice the geometry and segment joints move out of alignment with the result arm though. We saw this before in part 6. It's due to the spline curves double rotating with the arm, so we can fix this by selecting each of them and turning off the inherits transform attribute. However, recall from working on the leg in part 18 that this effect bleeds over into our IK solution. Fix it the same way as before, by displaying the result const group in the node editor, and using a blend colors node to toggle the effect of the orient constraint on and off, depending on the current IK-FK mode. The next thing we'll do is lock and hide any attributes we don't want the animator to touch. This includes the translation, scale, radius, and visibility of the FK controls. And everything on the FK const group. Then lock and hide the scale and visibility of the IK arm control, the translate, scale, radius, and visibility of the elbow FK arm control, and all the attributes on the elbow's locators. We should also hide all the space locators in the workspace. Next, add the shoulder joints to the result skeleton layer and the corresponding geometry to the geo layer. Add the segmented arm geometry to the geo layer while you're at it. The final point on our rigging checklist is that we need the arm to respond correctly to root transforms. While translation and rotation work fine, scaling in IK mode causes the arm to bend. From working on the legs in part 18, we know this is because we have yet to factor the root transform into our stretch calculations. Turn on Shapes in the outliner and select both the left shoulder and the left arm length measurement nodes. Open the node editor and show the connections. Create a pair of multiply divide nodes named Global Scale Left Arm Normalized div and Global Scale Left Shoulder Normalized div. Middle drag the Emma root transform control into the node editor and connect the Scale X attribute to both normalized nodes, Input 2X attributes. Next, feed the distance values of each distance node into the Input 1X attribute of their respective normalized nodes. Then connect the output of each into the driven key animation curve that drives the arm and shoulder's length, respectively. We also have to do this for the segmented joints too, so select them and display their connections. Create two more multiply divide nodes named global scale left upper arm normalized div and global scale left forearm normalized div. Use them to divide the normalized spline lengths by the character's global scale. Then feed those values into the sectioned forearm and upper arm joints. That fixes our root transform issue. This finishes up the arm rig. In the next movie, we'll begin work on the last unique body part, the hand.